Okay, so welcome to this specific class. This is another invited talk. Today it's great to have Paolo Perrone and Rob Cornish from the University of Oxford. They will talk about Markov categories, symmetries, and generative AI. And the lecture is split in two pieces. The first one is going to be delivered by Paolo Perrone and the second by Rob Cornish. So before we start, a quick introduction of both speakers. Paolo is a researcher at the University of Oxford. He got his PhD at the University of Leipzig, and then he worked for a while at the Max Planck Institute for Mathematics, and then spent time at York University in Toronto, and actually also here at MIT, back in the days working with David Spivak. I actually met him during the time he was here at MIT, and since then I got in touch and I followed his amazing work. And his research focuses on category theory and applications to probability and information theory. The second speaker is Rob Cornish, who is a Nightingale Bicentennial Research Fellow in the Department of Statistics at the University of Oxford, where he also got his PhD. And his research focuses on providing top-down formal guarantees about correctness and robustness of large-scale machine learning systems. So I think this is a great example of category theory all the way from the theoretical foundations to actually downstream applications. And that's why I invited both of them to give a talk. And let's make this interactive. So whenever you have questions, you can raise your hand and ask, both in the virtual and in the physical audience. And yeah, without further ado, guys, thank you so much again for giving this talk and this class. And I look forward to hearing more.
Thank you. Thank you for having us here. It's nice to see my team again, and kind of funny to see it from the other side now. So I'm going to talk about Markov categories, which are a recent framework to do, I want to say, probability and all things random using categories. Okay? Hopefully it's clear what I mean in a moment. So I'm going to talk about Markov category and see what it can tell us about situations of symmetry, and then I'm going to hand it over to Rob for some more concrete work. All right. So what is a Markov category? Intuitively, a Markov category is a category where you can think of morphisms as of having some kind of randomness. Maybe I should ask, can you see my mouse pointer?
Yes.
Okay. So the first example is the category which we call Finstock of stochastic matrices. What's the idea? Okay, I should also say these colored arrows are not the arrows of the category, okay? Capital A is an object, capital X is an object, those are finite sets, and this whole thing is a morphism, all right? So you can view this as probabilities of transitioning from little a to little x and so on in such a way that you see these are normalized to 1. So each one of these is a probability distribution, or equivalently, you can view this as a matrix whose columns sum to 1, okay? So this is a morphism of something that you can view as something as having some kind of randomness, right? You can go from A to X, or the probability of the X given A, if you want, is 1/2, and so on, all right? So how do you compose this? This has to say it's a category. Well, you see, what's the probability of going from little a to little k? Well, that's the probability of, say, from going from A to X and then from X to K, and so on for all the intermediate steps. That's exactly how you compose probabilities, say, in the Markov process. It's called the Chapman-Kolmogorov formula, and it's actually the usual row by column composition of matrices, okay? This makes this a category, okay? Also, probability measures are going to be columns of these matrices. So in particular, the vectors are exactly, the column vectors are exactly the probability measures or probability distributions, okay? That's the first example of a Markov category. And you see it's a little bit like a Markov process, but potentially more general. I should also maybe say Markov categories are not just for Markov processes. They are for all processes. It's just that the Markov ones are the base case, like the simplest ones. And so they're the easiest ones to represent, okay? All right. The second example is, now we move to continuous space. So instead of having single elements and transitioning from single elements to single elements, now, single elements tend to have probability 0. So we have to go from single elements to some events. So what's the probability now of transitioning from X to this subset. Okay, single points tends to be 1. So the equivalent of a stochastic matrix that is in continuous space is called a Markov kernel and takes measurable spaces. All right, so X with a sigma algebra A and Y with a sigma algebra B, and numbers which take an input, a set which is an output, and give us a number. Okay, and we want the probability measure here. We want this is a probability measure in each column, so to say, so for each X, and in this variable it's measurable, or equivalently integral. Okay, because again, we want to compose this. Before we had a sum, now we have an integral, but it's just the same thing as before, and so we want this integral to make sense. That's why we want the measurability. Okay.
Paolo, there is a question in the
Yes.
chat from Rita. I
Yes.
think it was from the last slide. I think it's important to get this right.
Sure.
At the beginning, it says, are A and X categories of random variables? I think here, maybe can you repeat that?
No. So the category, let's go back here. So the category here, Finstock has sets as objects, and these matrices as morphisms. Okay.
Yes.
So a random variable depends on how you want to model it, but if you just want the law of a random variable, then it's going to be a column of this matrix, or a morphism from a set with one element. So if we only had A here, we could in some sense view that as a random variable on X. Or equivalently, as I'm about to say, regular functions like deterministic are special cases of these morphisms. And if you want a random variable as like modeled as a deterministic map, then we have those two. Okay. So here it is. If you have a function from X to Y, then you can take this Markov kernel, which just says transition exactly to f of X with probability 1, then 0 otherwise. And so deterministic morphisms are going to be a special case. More of that in a moment. So this gives a functor from measurable functions to stochastic kernels. I hope this answers the question, but if not, please feel free to ask again. It's a good question. These are important things to clarify in the beginning.
Thank you, Paolo.
These are our first two examples. So categories where morphisms have some kind of intrinsic randomness in them, or variability of some kind. All right, so what's the categorical definition? So intuitively, we represent these morphisms with randomness as a string diagram. So a block with input X and output Y. So we usually write our diagrams as the morphisms are blocks and objects are wires. And we usually go from bottom to top, as in physics, or sometimes from left to right, as in computer science. Okay. So whenever you see something like this is a Markov kernel, or a stochastic matrix, or a probabilistic program, or something with some randomness from X to Y. Okay. The state, so a morphism from the monoidal unit has the interpretation of probability distribution, like before, a vector as opposed to a matrix, like just one column. We then have, for each object, a comonoid structure, which means two special maps, one from X to X times X, and one from X to the monoidal unit, which should represent this way. This map here has the interpretation of copying our information, copying our state of where we are. And this one discards it. And this has to satisfy some properties. So it has to be a comonoid. So like a monoid, but upside down. So you see, this looks a little bit like associativity. This kind of tells us that copying and then copying one of the two copies is the same thing as copying the other copy. That's some kind of associativity. This one here is like unitality, says that copying and discarding one of the copies is the same as doing nothing, the same as identity. And this one says that the two copies are interchangeable. Okay. Some more conditions. So this is a compatibility with the tensor product. So the copy of the tensor is the tensor of the copy. And then we have this other condition, which this one you can actually not assume, but it simplifies things a lot. It has to do with normalized probabilities as opposed to just measures. So this says that for every program, say, then applying your program to an input and discarding the output is the same thing as discarding the input to begin with. Okay? Sometimes you want this, sometimes you don't. Like, for example, if your program has a cost of processing, then this is not the same, right? So sometimes you want this, sometimes you don't. It's not very important, but for this talk, we will not. So So we will assume these are additional numbers. So here is the actual definition. So a Markov category is a symmetric monoidal category where each object is equipped with some distinguished maps, which represent in this way, satisfying these axioms. All right. So that's the definition of a Markov category. And well, we just saw two examples: stochastic matrices and stochastic kernels. Deterministic functions, so set, the category of sets is also a special case, but we will see a very trivial case because there is no actual randomness. All right. Any questions so far? No. You're always free to interrupt. So what is the copy map for Finstock, for stochastic matrices? Well, we want to say that from X we copy, so we take XX, right? Two copies of X. So as a stochastic matrix, well, as a function is something like this. You see, we go from X to X times X and go to the diagonal. So as a stochastic matrix, it says the probability of going from X to X times X is 1, and the rest is 0, and so on. For stock, it's the same, except in continuous. So how do you say that in measure theory? Well, you embed X into the diagonal here, which means that the probability of ending up in A times B is the same thing as saying that X is in A and in B. So X is in the intersection of A and B. So this is the same thing as above, except in continuous space. And everything else, all right? So let's now do some probability. So first of all, I said that this is modeling random things. So what does it mean random? It's easier to see and to say what is not random. We call a process deterministic if processing and then copying the results is the same thing as copying the input and applying the process twice. Let me give a little example here. First of all, in set function, every morphism function is deterministic. So take X, apply F, and then copy. Okay, so that's two copies, f of X, f of X. Or take X, copy. So X now we have two copies here. And now apply F to both copies. You see the result is the same. We have the order pair f of X, f of X. No difference.
So I have a question.
Yes.
Can we go back to the previous slide? I was trying to figure out, so in the definition of category stock, if you take the monoidal product of two objects, X and Y, and do we restrict the measure on this monoidal product to be only the measure of, only the product of two measures on the individual object, or not?
No, and that's going to be crucial. No, because we take any measure on the product.
Okay, so here it's just an example of we actually take the product of two sets, but we can actually take any measure on this product set.
Yes.
Okay, thank you.
More of that in a moment, actually. But yeah, thanks. That's a good question. Okay. All right, so in set, then you see this is deterministic because these two things are equal. Now, take now this thing instead. Imagine some kind of probabilistic program that takes a number, flips a coin, and if it's heads, it adds 2, and if it tails, it adds 3. Okay? Now, we could first, suppose we start with the number 2, we flip a coin, and with probability 1/2, we get 4, or probability 1/2, we get 5, right? Because we add either 2 or 3. So, and then we copy the result. So we get an ordered pair with two numbers, but these two numbers are guaranteed to be the same. We don't know which number we get, either 4 or 5, but we know they're going to be equal. On the other hand, on the right-hand side, we have to flip two coins, or like flip twice, okay? So you see here, anything could happen. We start with 2, and maybe the first time we get +2, and the second time we get +3. So this 4 or 5 is possible now, okay? So now, on the left, we have perfect correlation. On the right, we have conditional independence given the input. And the fact that these are different is exactly a feature of the fact that things are random. Okay, we take this as a definition, right? So let's do the math. In stock and in Finstock, actually, we can see what it means that these two things are equal. That's the equation. We can do the math, and that exactly says that for every x and y, f of y given x is equal to its square. So it's either 0 or 1. So those are exactly those matrices whose entries are just 0 or 1. There's no 1/2, no 1/3. So exactly those things that are deterministic in the number sense. Okay. Same thing for Markov kernels, all right? And I have to say, I did not invent Markov categories. But this is, when I saw this, this is when I was sold to them. And I decided to work on them. Because I was thinking, this idea of copying information before and after really encodes randomness. Because this recovers the probabilistic definition. Right? This recovers, so to say, the fact that in the numbers, these things are deterministic. Okay? And for states, again, the condition looks like this, and again tells you that the probability pretty much is a Dirac delta or something very similar. Okay. Another thing we can do is to talk about independence. So what does it mean that the probability of the product is the product of the probabilities? Well, that is not always true, but when it's true, in Finstock, it looks like this, right? And in string diagrams, it looks exactly like this. So it kind of says that P could be like split along those lines in a sense, is equal to the tensor product in the monoidal category sense of P of X and discard Y, that's the marginal, P of X, and P of discard X and Y. Okay? Joint marginals, and when the joint is the product of the marginal, you say that these things are equal, and they are independent. Similar is conditional independence, where now we say that f of xy given A is the product of these two, and now we have to use the copy map. Because on the right-hand side, you see that we have f of x given A and f of y given A. And that's the same A here and here. So it's not A and A prime. We're using A twice. So we need to copy this information, and that's how it appears. Okay. Maybe I should ask, I don't know the background in probability of the audience. Is everybody familiar with what conditional independence is as opposed to independence?
Everyone, okay?
No, if you could just do a brief explanation.
I couldn't hear. Can somebody?
Yeah, someone needs a brief explanation of
All right, let's have a brief explanation. Okay, so since I'm Italian, let's use this example. Suppose that you sample a bunch of data about how much people tend to eat pizza and how much people tend to drink espresso. Okay? And you see from the data here, there seems to be some correlation. Okay? We're like, oh, wait. It seems that people that tend to eat a lot of pizza also tend to drink a lot of espresso. Have we discovered something about human nature? Okay? Then you look closely and you notice actually that half of these people come from Italy and half of these people come from the rest of the world. And you see the green points are actually almost distributed along a circle. So once you fix the country of these people to be Italy, you don't see any relation between pizza and espresso. Both are globally higher, but they're not correlated anymore. And the same thing happens with the red points, okay? So what's going on here? You have explained away that correlation. You have explained that given where people come from, so if you fix some hidden information, in this case, country of origin, then suddenly these two things are independent, or I mean, in practice, approximately independent, okay? So the whole distribution here from X and Y, so X is pizza and Y is espresso, cannot be split completely. But the part here, F, can be split, okay? So P cannot be split, but the output of P, which is the country of origin, that's A, given the output of P, given the country of origin, you can split. So you can split until here, okay? Maybe I should also mention, these are not real data. Pizza is actually more popular than espresso, so I guess real data would be a lot more skewed to the right. Everybody likes pizza, come on. All right, but I hope it's clear what's going on. So given something, then things will start to be independent. And this is exactly reflected by the string diagram. So until when can you split your diagram? Well, in this case, until this hidden there. All right. So you can really do, there's some theorem to show that things are conditionally independent if and only if you can split the diagram. So it's really, there's a correspondence between the categorical decomposition and the statistical decomposition, which is 1-to-1. So you can actually do statistical inference using these string diagrams. All right. Any more questions?
Yeah, it's clear.
Great. All right. Another thing you can do is conditioning. So conditional distribution, given a joint distribution here of X and Y, a conditional distribution is like basically turning this inference, this information flow from X to Y into an actual morphism. So a morphism from X to Y, possibly random, such that, well, I want to say such that P of X and Y is P of X times P of Y given X. So something like a base form. Okay, so in Finstock it looks like this, in Borastock it looks like this. This is the string diagram. So you can do conditionals just in terms of string diagrams, and that simplify a lot all the time. So people do conditional. Okay. All right, that's the end of my quick overview on Markov categories. Let me just say, you can do a lot of probability and related things using Markov categories. Here are some papers. We can, for example, prove Definity's theorem just by means of string diagrams. We can prove stuff about martingale, sufficient statistics, statistical experiments, and a lot of other things. So here are some results that have been done, that have been proven in the past few years, not just by me, also by a bunch of other people, okay? If there's interest, I can explain a little bit more on those. But for the purpose of this talk, let me move on to the next topic, which is symmetry. So you might know by now that one of the situations where category theory really shines is in situations of symmetry. Category theory is somehow automatically taking care of the symmetries and invariances of things in a very elegant way. And so Markov categories are very good for showing randomness in situations of symmetry, okay? So here is a little motivation for what I mean. So I have a little program in Touch Designer, which was provided by my partner, Miranda Silvermar, who I really want to thank. So let's move to Touch Designer. So look what's going on here. I have, can everybody see this program? It looks a little bit like a string diagram. All right.
Yes.
So I start with an image of a blurry banana. Okay. And then I have here an implementation of pretty much stable diffusion. It's called stream diffusion, which tries to give me an actual image of banana from training data, sometimes a drawing, and tries to, unblur this, okay? And of course, as you know, generative algorithms, the best thing about them is that if you're not satisfied with what you get, you can just sample again, and they give you a different image, okay? So I'm on a laptop here. It's a little slow, but you see I click on sample, and I get a new banana, okay? Each time. Okay, this one is better. Now, what I want to say is that if I rotate my initial image, then I should get a rotated banana. However, this is generative. So now I'm going to rotate, let's say, 90 degrees. And you see, I don't get the same banana as before because this is generative. There's no way, this is going to be exactly the rotation of the previous banana, right? But of course, it's oriented in the way I want. However, what is true, though, is that if I keep sampling, then I get different bananas, and the statistics of my rotated bananas, okay, are going to be similar to the unrotated banana. You see, sometimes it's smooth, sometimes it's drawn, sometimes it's more green, sometimes you see now it's more like a clip art. And if I change the angle of rotation, again, I get a different banana, but the statistics of the banana, the distribution it follows, is still kind of the same. Sometimes it's a clip art. If you keep sampling, it's statistically speaking, respecting the symmetry of my problem. Does anybody see what's going on here? So the statistics is symmetric. Okay. So I want to say that, this diffusion algorithm that generates my things is stochastic, but respects the symmetry, of course, approximately. So let's get back to that. What is symmetry? And for those of you that don't know, symmetry means invariant under something. So what does it mean that these four figures are invariant? It means that there are transformations, in this case rotations, by 120 degrees, 90, 72, and 60, which leaves them invariant. So a symmetry of an object is a set of transformations that can be composed, contains the doing nothing, and can be inverted. So it leaves it as it is. The mathematical definition is a group, you might know that. In terms of string diagrams, is an operation like this, which lets you compose two operations, okay? And it's associative. It has a neutral element, so which we can write like this. So it's like a special element, such that multiplying by that is the same as doing nothing, and such that it has inverses, which in string diagram, you might use start with some G and get your inverse. And so multiplying, you copy G, you see we're using G twice here. One of the two is inverted, one of the two is not, and you multiply them. And that's the same thing as discarding G and just applying the identity. You see E here is not used G, so we have to discard it. Okay? So that's how you write a group using string diagrams. And in Markov categories, it's very important. Number one, this deterministic. Okay? There's a condition for Markov categories called positivity. So you want deterministic groups in your Markov categories. All right. Now, how do groups act? A group action is a morphism like this. So it has two input wires. One takes like the transformation G, then it takes some input and gives you the transformed output. Okay, we saw this in Touch Designer. Look at this. The rotation action took an input blurry banana and an angle and gives you a rotated output. You see the two purple wires are the X and the green wire is the G. Okay, so this is a group action. All right, let's go back. So it's something like that, satisfying some. For example, if the angle is 0, that's the same as doing nothing, right? We don't rotate any banana, and the compatibility with multiplication. All right. All right. So now, a map is called invariant if you rotate your banana, the output is exactly the same. It's as if you discard what G is doing. Okay. That's not our situation before. Remember, before what we were having is if you rotate the banana, it's not like the output is the same. The output is rotated of the same amount. So that's how you write this in string diagrams. So a morphism is called equivariant if you rotate the input, then it's the same as just applying your program and rotating the input. So something like this. So this is a map that respects the symmetry. Imagine something that collapses these petals down to just 2 lines. If you rotate this, you also rotate the line. So this respects the symmetry. Okay. So on this figure, rotations act. On this figure, rotation act, and this respects the symmetry. All right. If F is not deterministic, that's what just means that things are respecting the symmetry, but only up to this, only up to their statistics, only up to some sampling. Okay, just as I showed the banana before. So this map here that we saw in Touch Designer, this is equivariant, but not deterministic. Okay, so things respect the symmetry, but only, so to say, if you sample enough. All right. Is this clear? All right. So in Markov categories, you don't just talk about groups, actions, and equivariance. Actually, there's a lot more you can do. You can do very advanced group theory, group homomorphisms, orbits, cosets, continuous actions, compactness, semi-direct products. Group theory and category theory go very much hand in hand. Actually, they're basically the same larger theory, and Markov categories are not an exception here. Okay, see the paper for more information on this. So to learn more about Markov categories, I recommend to look at this paper by myself in section 1. There is a little introduction to Markov category aimed at information theorists. To learn more about Markov categories and equivariance, look at section 3 of this paper by Rob. To learn more about some probability, like some more hardcore probability with Markov categories, I recommend this paper by Tobias Fritz. So that's the end of my part. I think if there aren't no more questions for me, I will hand it over to Rob.
Any questions for Paolo?
All right. Thank you so much. And let me unshare my screen. All right.
Cool. Okay, let me try to share my screen. This can be a bit tricky on Linux. So
Can somebody make Rob co-host, please?
Oh, yes. I cannot see, so make a host. Okay, now make a host.
is that visible to everyone?
Yes.
Okay, amazing. Cool. Well, yeah, thank you very much for the opportunity to present today. It's a real honor. I guess to kind of motivate to some extent what I'm going to talk about, I'll just slightly recap. So I suppose maybe about myself, I'm sort of a machine learning person. So I really come to this from a machine learning angle. I'm going to kind of emphasize that in this talk. I'm going to start out, I suppose, by giving like a machine learning kind of practitioner's perspective on equivariance. I think is going to complement Paolo's. So here's a problem where you often want, in a machine learning context, where you want a property like equivariance to hold. So imagine that you've got a problem where you have images of cats as input, and you would like a neural network that basically takes an image of a cat and produces a binary mask that has a black pixel in every location where there's a cat in the original image. So intuitively, it's sort of clear that you would want a neural network that does this task to basically satisfy the equivariance property shown here, where if you sort of take your cat input and translate it and then map it through your neural network like this, that should give you kind of the same thing as if you first of all take your cat, map it through the neural network, and then translate the result. Sort of a priori, like a sensible neural network ought to do something like this. It seems would be reasonable. And so, as Paolo said, the way you can formulate properties like this is via the notion of equivariance. So this is what I guess people use in the literature to sort of reason about properties like this. So you will say that a neural network that takes inputs in X and gives you outputs in Y is equivariant with respect to the action of a group if basically this condition here holds. So you take an element in your group, this would be, in the cat case, a translation, you apply that element, you apply that transformation to your input, your picture of a cat, and then you map that through your neural net. That should give you the same thing as if you first of all take your picture of a cat, map it through your neural net, and then apply this transformation to the result. So yeah, in the example here, X is the space of images and Y is the space of binarizations of those images, and then G is the group of translations. But this property is by no means just limited to problems involving cats. There's many other examples in machine learning where this arises. So for example, processing like point cloud data, it's very common to want a neural network to in some way sort of respect kind of geometric transformations of that data, or perhaps reorderings of the points in that point cloud in some way. Similarly for like protein data, sort of protein, if you sort of rigidly transform it in space, you get kind of the same protein. So this naturally leads to equivariance constraints like the one just mentioned. And similarly for kind of graph structured data as well. There's this broad field in machine learning that you might have heard of called geometric deep learning, which really studies many different examples where this arises and kind of neural network architectures that will give you the kind of desired behavior. And I guess that kind of leads to like the actual kind of problem here, which is basically like, how do you actually parameterize a neural network that has an equivariance property like this? So suppose you've been given a group acting on some X and Y. How do you make sure that your neural network architecture actually satisfies the equivariance constraint I mentioned at the beginning? Because by default, off-the-shelf neural networks typically will not satisfy such a constraint a priori. So you need to sort of do something to kind of make sure that that actually holds. And there's really two main approaches that people use to enforce this, intrinsic equivariance and symmetrization. I'm going to mention both of these briefly now. So intrinsic models, intrinsic methods, I should say, basically take the neural network that you write down to have the following form. So basically they sort of parameterize a set of equivariant linear layers and a set of equivariant nonlinear layers, or a collection or family of these kinds of layers. And then they take the overall model to be a big composition of these kind of primitive equivariant components. And you can check that basically the composition of equivariant layers is self-equivariant. And so by construction, this necessarily gives you an overall network that has the equivariance constraint that you're interested in. It's a very natural idea. It's very popular in the literature, but it does have some potential limitations in some cases. So, for example, it often requires some hand engineering for each specific group and action of interest. And there are sort of many different configurations or many different sorts of choices that people want to make for these things. And so you sort of end up having to implement many different architectures to account for each possibility. The nonlinear layers as well in this approach can often also be quite ad hoc. There's generally very good theory for how to get nice equivariant linear layers using like representation theory, but the nonlinear layers seem a bit kind of out of scope of that. And so often you sort of have to do some trick and they don't often necessarily scale very well. And so as a result, these models can in some cases be hard to scale. And so that's a potential problem. So there's this other approach to obtaining equivariance that you might call instead symmetrization. And so the way these models work, or these methods work, I should say, is that they basically start with a totally off-the-shelf, unconstrained neural network. They don't start with these kind of primitive equivariant linear and nonlinear layers. They start with basically a full neural network that can be kind of like an arbitrary, transformer or CNN or some potentially very crazy model. And then they kind of do something to it. They sort of pass it through some procedure that gives you an equivariant model as a result. They sort of symmetrize the model in some way. And the idea is that they do this in a way that like doesn't require you to sort of look inside the model. So it's compatible with these very powerful architectures. And the overall kind of motivation is to try to get the best of both worlds, where you've basically got, on the one hand, a sort of powerful kind of backbone architecture that can be very flexible, but at the same time, you still obtain the equivariance constraint that you're interested in. Okay, and so how does something like this, how could this actually work in practice? Here's kind of an early example of an approach like this to kind of keep in mind to get a flavor for how this could work. It's called Generative pooling. So imagine you want to write down a neural network that takes a sequence of n inputs that are valued in X and gives you like a real valued output. So it's a sequence, it predicts a value based on a sequence of inputs. And often for these kinds of problems, you might want a model that is invariant with respect to reorderings of that input sequence. It sort of processes the input sequence as a set rather than as a sort of a list. And so what Generative pooling does is basically it starts with an arbitrary neural network F that is that takes these n inputs and then just sums over all possible configurations, all possible orderings, I should say, of those inputs. You end up with a model that looks like this, and you can check that basically this thing is always permutation invariant. That gives you sort of like a flavor of how this sort of thing might be possible. There's some other examples in the literature, including very recently. I won't go through these, but basically for certain choices of the components involved here, so F, H, and P, you can show that for any sort of backbone neural network F that you choose, these models here that you get are appropriately equivariant. Okay, and here F again can be very complex. It can be an off-the-shelf unconstrained neural network. It's potentially very powerful. Okay, so this is great, but there's some sort of open research questions here. So one is basically, where do these symmetrization methods come from? So essentially, like this previous work is really kind of just written down these methods and said essentially, and just basically shown that they are in fact equivariant. So there's a question of like, where do they actually come from? And that's kind of interesting as like a theoretical exercise. It's a good sort of like conceptual problem, but it's also kind of a practical problem as well, because if you can kind of answer this question, you can then basically determine whether there are other possibilities. Like if you can figure out sort of like the whole space of sort of every possible symmetrization procedure that you could write down, you can then kind of choose the one that is best for your particular application. It gives you kind of the flexibility to make that choice. And in addition, there's a question here around stochastic models. So these previous models were all deterministic, or they all considered backbone neural networks that were deterministic, and the goal was to obtain an overall neural network that was deterministic as well. But as Paolo mentioned, often it's interesting to have a model that is stochastically equivariant, a stochastic model that is equivariant in a particular sense. So I'm going to just slightly recap that here, again, using the concept of bananas. Basically, you can imagine here you've got a problem where you have a model that is like a noisy banana detector. Okay, so you take as input an image with a banana in it, and the goal is to produce as output the location of that banana in the input image. And this model is allowed to be noisy. So if you rerun this on the same input, it can give you different results each time. So here on the right, you can see like the result. You can imagine that this is like a cloud of points of many different predictions that this model has made as to where the banana is. So sometimes it predicts over here, sometimes over here, sometimes over here. So for these kinds of models, it's natural to require that this cloud of points vary equivariantly with the group action. So if you sort of take your banana image, you apply your noisy banana detector very many times, and then translate that whole cloud of points, that whole cloud of predictions, that should give you the same thing as, first of all, translating your banana and then getting your cloud of predictions as well. So this is, again, to kind of reiterate Paolo's explanation, this is not necessarily talking about equivariance in kind of a pointwise sense. It's not saying that for any individual prediction that your model makes that you've got some suitable equivariance property. It's saying that sort of on average, as you take many, many predictions, this whole distribution varies in the right way, basically as shown here. So this is a property that it turns out people care about in applications as well. And this previous work on symmetrization hasn't directly given a method that can work on stochastic models like this. And so what I'm going to talk about now is basically this paper here, which gives a general theory of symmetrization of this, that involves this previous work, or encompasses this previous work, but also then extends to stochastic models as well, and basically allows us to obtain the equivariance constraint that I just mentioned. Okay, and so here comes the category theory, which I guess is what you've been waiting for. So the theory in this paper is developed in terms of Markov categories. So I think there's a natural and important question to ask here, which is like, why do this? I think it's, it's sort of it's important to kind of approach this with some degree of care. Like, is this actually obtaining some benefit for us, or like, what's the motivation for doing this, as opposed to being kind of like an intellectual exercise? And my own view on this is basically the following. So I think in machine learning, we often talk about like the model, but I think that in practice, there often turns out to be kind of three models. So there is sort of the mental model that people have in their heads about how the world is, and their intuitions about how their method works and so on. Typically, then they write down like a mathematical model that they hope kind of corresponds to the mental model in some way. They sort of try to write down in symbols on the page like some representation of this original model, and then ultimately these days, inevitably, you sort of end up writing down a computational model, which typically is like tries to represent this mathematical model in code in some way. And I think perhaps everyone's had the experience. In my own experience, these three are often very distinct. The mental model doesn't really match the mathematical model, and the computational model is kind of different from both of those. And in the context of machine learning, I think a major reason for this is measure theory. So particularly when there's probabilistic reasoning involved. So probability is really very common nowadays for machine learning. It kind of comes up in most applications. But the actual kind of theoretical foundations of probability, as no doubt you're aware, are very technical and complex. And so in practice, like people don't tend to actually work with measure theory in machine learning papers or machine learning research. I think with very good reason, because it's just too dense and technical to kind of express the kind of complex situations that they care about. And so what people end up doing instead is working with this kind of semi-formal density notation that looks like this, that you've probably seen. You sort of write everything in this way instead. And this works very well for a remarkable number of things, but it does start to become kind of complex in some situations. So here's kind of a somewhat unfair example, but perhaps not completely unfair. So this is trying to depict what would be involved with sampling from the encoder of a conditional variational autoencoder and then mapping it back through the decoder. This is a little bit hard to really see what's actually going on here. You've got kind of X repeated 3 times. You've got Z repeated twice. Machine learning people learn how to kind of like look at this and understand what is meant basically by convention, but it's sort of at the point here where like the symbols on the page don't actually match the actual model that they're reasoning about. There's sort of just these conventions that kind of hold everything in check rather than, I guess, the formalism itself. An example for the context of symmetries is equivariance. So if you want to write down stochastic equivariance in terms of densities, this is the condition that people use in the literature. There's actually even a caveat with this as well, but you can show that if this caveat holds, this thing here corresponds to the example of the banana detector that I mentioned earlier. But this, to me, doesn't really match the conceptual notion of equivariance that Paolo described, this idea of like, you've got a morphism K and you sort of do something to the input, and that's the same thing as like mapping through your morphism and then doing something to the output. Here, the group is sort of acting both, it's acting on the same side in both input and output. It kind of doesn't really correspond to this input-output interpretation that you sort of intuitively have. And so where Markov categories can come in and really, spare you pain, essentially, is to abstract away a lot of these kind of measure theoretic low-level details, but maintain rigor and sort of still allow you to reason very carefully about these kinds of complex systems. So the theory then becomes very conceptual and diagrammatic and much closer to the mental and computational models. So great. There's many examples, I would say now. I mean, Paolo gave a great list of references, which I highly encourage going through, of Markov categories, and I suppose category theory more generally, giving kind of retrospective simplifications of existing theory. But then I suppose the test of a good theory is like, can it lead to something new? Can it lead to like new methodology that wasn't previously known? And I guess that's the one of the messages of this paper I'm going to talk about, is basically the answer is yes, you can actually use Markov categories to address sort of real machine learning problems and get something new as a result. So let me talk about that now. I suppose the mention in passing, it's sort of anecdotal evidence, but it's actually how this paper came about. Like, I didn't set out to write this or to sort of to work on symmetrization. I was working on some other kind of more theoretical questions using Markov categories, and the conceptual clarity that the theory afforded me basically led to, I guess, this approach that I'm going to talk about now. So it's kind of a data point that shows that this strategy can be profitable. Okay, so to sort of slightly recap, we want to talk about symmetrization in general Markov categories. That's kind of the goal here. So to just reiterate again, in a general Markov category C, there is a way to talk about analogs of, or generalizations of, kind of classical groups. So we say that a group in C is an object equipped with some multiplication operation, some identity operation, and some inversion operation that look like this. And we can say that an action then is just some morphism that has this form. It takes a G, which we think of as taking as like an element of the group. And it takes an X, and it basically, we think of it sort of applying this input to X, and it gives you an X as output, like, for example, transforming the banana in some way. X is the banana and G is the transformation. Then there's some axioms that they satisfy, which Paolo mentioned. Great. So with this, again, we can talk about equivariance. To reiterate this, this is the definition. You say that a morphism in a Markov category is equivariant if applying the action to the input and then mapping through the morphism is the same as mapping through the morphism and applying to the output. You can swap the ordering of the actions before and after the morphism. Okay, and then if you instantiate this, not in an abstract Markov category, but in a Markov category with whose morphisms are actually functions, then this gives you back the usual definition of equivariance. But if you instantiate this differently in a category of Markov kernels, such as Stoch that Paolo mentioned, then this gives you a notion of stochastic equivariance that turns out to correspond to the banana example from earlier as well. So we can kind of talk about, we can sort of reason abstractly in a general Markov category and then instantiate the theory down to the deterministic setting or the stochastic setting, depending on what the application requires. Okay, so great. You can check that the composition of equivariant morphisms is itself equivariant. So that leads then to the following result. Basically, given a group in a Markov category C, there is always another category called CG, where the objects are pairs, where the first element is an object in the original category, and the second element is an action of G on that object. So these, you think of these as like G objects. It's an object of C equipped with an action. Right, so that's the objects of CG. What are the morphisms? The morphisms of CG we're going to define to be equivariant morphisms in C with respect to these actions that have been specified. So previously between X and Y, we had sort of every morphism in C. Now between X alpha X and Y alpha Y, we're only going to have the morphisms that are equivariant with respect to this. Okay, and I said actually this is a Markov category. There's a bit more to show here, but it turns out to be true. Essentially, so you need to kind of, this additional structure that a Markov category possesses that Paolo described, you need to show that that structure also carries over, but it turns out that you can do that in a kind of canonical way. And so, this CG actually is a Markov category, not just the category. Great. Now that leads us naturally to the following definition. So we're now in a position to actually define what a symmetrization procedure actually is. So this is not something that really was done explicitly in the literature, but the Markov categories framework we're using really provides a very sort of streamlined way of actually doing this. So what we're going to say is that a symmetrization procedure is just any function that maps this set to this set. So I'm using the notation here. You've probably seen this. The set of morphisms from X to Y in a category C, we're going to denote CXY. So sim here, a symmetrization procedure, takes as input an arbitrary morphism in C from X to Y and gives you as output a morphism from this thing to that thing. If you think back to what the definition of CG was, that is by definition an equivariant morphism with respect to these. So it takes an unconstrained morphism as input and gives you an equivariant morphism as output. And it seems a very natural definition of of what it would mean to be a symmetrization procedure. It's kind of, we're not imposing any constraints on this function. We're just saying it's some function of this form. And it's hard to kind of imagine sort of more generality in this example that you might want here. So it's quite a comprehensive definition. And it's also quite nice that with this nice sort of basis in Markov category theory, we can actually really represent everything like in kind of like one definition here. Like all of the moving parts are kind of explicitly denoted. We've got like the background Markov category that we're using. Are we dealing with Markov kernels? Are we dealing with functions, etc.? We've got the objects X and Y. We've got the group denoted here, and we've got the actions all kind of explicitly represented. Great. Okay, and as I said, we're not really imposing any constraints on sim here. We're just saying it can be any function of this form. And that seems like, there's sort of no hope of kind of working with this. It might seem that that's kind of like too general. But actually, like, despite this generality, we're going to provide a characterization of all functions of this form in a sort of meaningful way that can actually lead to something concrete. So I'm gonna do that next. And sort of the key result for this is basically this here. So it turns out that for all of the components involved here, every choice of C, X, Y, G, etc., there is always the bijection of this form here. So bijection that takes an arbitrary morphism from X to Y in C and gives you a morphism from G times X to Y in CG that is suitably equivariant. I haven't told you actually what the action of this object here is, but it turns out you can do that in a canonical way. You can kind of just sort of take my word for that, essentially. But the actual definition of this bijection is explicitly shown here. So it takes X, so it takes K in this set here, and it returns this morphism here, which turns out to be equivariant in the appropriate sense for this set up here. So here we're just like wrapping K in essentially these components here that involve, like, first of all, the group inversion operation, these actions alpha X and alpha Y that we have to work with. And it turns out this is a bijection, so everything in this set here can be expressed uniquely in this form for some choice of K from X to Y. Okay, so now I guess another nice thing about using category theory for this is that we get a very sort of clean explanation of like what's going on here. So this is not just kind of something that happens in a sense by chance. It's actually something that comes about in a very structured way as a result of an adjunction that exists between C and the category CG. So if you've seen adjunctions before, this is kind of like obviously a standard concept in category theory. Essentially here we have this sort of natural, this kind of canonical functor from CG to C that basically just begets the action associated with an input. It just maps it maps X alpha to just X. And it turns out that this thing has a left adjoint F. And by definition of, from what it means to be a left adjoint, that basically allows you to essentially move this U over to this left-hand side here. That's kind of the defining property of adjunctions. And then it turns out that this composite functor here can be expressed as this product. This is just to give you definitely don't need to understand this in detail for the rest of the talk, but like this is to give you a flavor that you get sort of very nice explanation or sort of nice kind of theory that, or yeah, I guess explanation for like where this result actually comes from as a result of using this framework. Okay, so we've got this bijection. How does that help us with symmetrization? So as a result, we get this kind of straightforward corollary here. So every symmetrization procedure, remember we said a symmetrization procedure is a function of this form. Okay, it takes an arbitrary morphism X to Y and gives you one that's suitably equivariant. As a result of this bijection, every such function can be expressed as this two-step process here, where we first of all start with an arbitrary morphism X to Y, we apply the bijection that I just showed you, and then we apply some function here from this thing to that thing. Okay, so every function here from here to here can be written like this for some choice of this second step. Basically because like if these two are in bijective correspondence, you can think of them as like the same set. So every function that goes from here to here corresponds to a function that goes from here to here and vice versa. Okay, so how do we actually, if we want to implement this in practice, we actually need to choose this function here for the second step. How can we do that? Well, if we're not willing to make any more assumptions about the groups or the category or the actions or anything else involved, there's really only one kind of obvious choice here, and that is precomposition. So we want a function that takes as input a morphism in this set and gives us a morphism in this set here. So it takes a K that looks like this, and it needs to give us a morphism from X to Y. How can we do that? Well, basically what we're going to do is we're going to choose some gamma that goes from X alpha to this product, and then just compose the two. We start with K and we return K of gamma. And that gets us a function that like maps K in this set to then K of gamma in this set here. And as I say, this is essentially the only obvious choice you can make if you want a kind of general purpose procedure that doesn't require any more structure here. Okay, how can we choose gamma? This is now added like an additional choice we need to make. There's this sort of natural requirement that you might want for a symmetrization procedure, which is that if the morphism you give it is already equivariant, then it should just return that morphism. You can say it's sort of stable on equivariant inputs. And you can show that basically that property holds if and only if this precomposition morphism has this form here, where it essentially doesn't modify the X input. So it essentially reduces to this choice of gamma that goes from X to G rather than into this product space. Great. Okay, so now we're in a position to give like an end-to-end procedure for symmetrization. That sort of, in a sense, I've argued is kind of like the only obvious way you can do symmetrization in a general Markov category. So having chosen your gamma, the overall procedure then becomes the following. You first of all start with your morphism K, you apply this bijection that I mentioned, and then you do this precomposition step where this gamma morphism is appearing down here. This gets you from an arbitrary morphism that has no equivariance guarantees at all into one that is equivariant with respect to these actions that you've chosen. This always works in any Markov category C. Okay, so let's now instantiate this result concretely. We're doing it in a sort of abstract Markov category up to now, but now we can do it. We can sort of like make this really concrete. If we instantiate this in the Markov category of sets and functions, so the morphisms are just typical functions, then we get this result here that says if you've got a group acting on X and Y and any function X to Y, and you've got a suitable gamma, then this function here defines an equivariant function X to Y. And this turns out to exactly recover one of these earlier methods that I mentioned called canonicalization from the literature. But by instantiating things differently, we also get something new. We get something that kind of wasn't previously known in this literature, and that's a procedure for stochastic symmetrization. So we're going to instantiate this now not in the Markov category of sets and functions, but we're going to instantiate it in the Markov category of measurable spaces and Markov kernels. So the morphisms now are sort of functions with randomness involved. And this is the result that you get in that case. So if G is any measurable group acting measurably on X and Y, there's these technical caveats you have to take into account, but Markov categories kind of lets you just avoid those. You don't have to worry about this. But we instantiate that these caveats appear. Then if K is any Markov kernel and gamma is any suitably equivariant Markov kernel as well, then this sampling process here defines a stochastically equivariant Markov kernel. So here you can kind of, if you squint at this, you can sort of convince yourself we're sort of doing basically what that string diagram on a previous slide showed. We're starting with X, we're sampling from gamma, we're sampling G from gamma, we're applying that output of gamma to X and then mapping it through K and then also applying it to the output. That's basically what's going on here. We start with X, map through gamma and apply it to the input and so on. So you can sort of read off this sampling procedure from this string diagram here. And again, I mean, this is nice because if you wanted to prove this, so it's nice because I guess this is like a new procedure, but it's also nice because if you wanted to show this kind of classically, you would need to technically write down a function of this form, give it sort of rigorous measure theoretic like definition of a Markov kernel, which is just really a technical exercise that I think doesn't have much conceptual value. This way you sort of avoid that. You can kind of just write this down. You sort of obtain this for free and you get the full kind of conceptual picture. You don't have to worry about these kind of low-level details as a result. Okay, cool. So then just to mention quickly here, that's sort of, I guess, the sort of base level or entry level kind of approach to symmetrization from the paper. I guess Markov categories really let you say a lot more. And I guess I can kind of refer you to the paper if that's something that interests you. Some of the things it lets you talk about is basically if you want to get a procedure that actually outputs a deterministic morphism, there's kind of a natural way to do that via an averaging step. I've kind of I've not mentioned that, but if you sort of if you add that into this process, then you also recover essentially every other method that I'm aware of for symmetrization that people have proposed in the deterministic context. so technically this part actually isn't using Markov categories directly, although there's a natural way that you could kind of encompass it in that theory if you wanted to. But what it definitely lets you talk about are kind of these components here. So I've sort of described symmetrization of like arbitrary morphisms in your Markov category. A more general problem would be start with a morphism that's already kind of partially equivariant in some sense and sort of upgrade it to become equivariant with respect to the full group. So maybe start with a morphism that's like equivariant with respect to a subgroup and then upgrade it to be equivariant with respect to the full group. And so you can formulate that in a nice way using Markov categories as something you can call symmetrization along a homomorphism. Gives you sort of additional flexibility. You can define kind of more general symmetrization procedures than you otherwise could. And this is where it becomes, I think, this sort of involves cosets and kind of sort of additional constructions from group theory that when they interact with measure theory become, I would claim, really quite intractably difficult to work with in a rigorous way if you want to sort of actually obtain this sort of a result analogous to this one here. So this one, arguably, using classical methods, you can just sort of crunch through that and it kind of works out. Admittedly, it's not how like I sort of came about this method. It's not easy necessarily to see that a priori, but you can do that. Once you start talking about cosets and these things, it does become much harder to actually do in a careful, sort of rigorous way. There's some other extensions here as well, and also many examples that you can sort of encompass in this framework as well. And I think this is really where you see kind of the power of Markov categories, is that like it's kind of hard for me to convey in this talk, but basically the framework lets you talk about all of these things in a very systematic way. You can kind of use the same notation, the same definitions, and it all just kind of works, as opposed to kind of needing to sort of stretch your theory and kind of be hand-wavy about things. The symbols that you write down as part of this really do match. They're sort of actually correct, and they sort of do match, I guess, what you want to say. It's much closer to something that you could imagine formalizing on a computer than I think the traditional approach. Even when you want to describe sort of many quite heterogeneous scenarios. Great, okay, so that's that. I'll just mention briefly some numerical results. This is not just kind of like a sort of theoretical exercise. You can actually kind of run these methods and get something new. So the method of one of these earlier symmetrization procedures for deterministic morphisms required a stochastically equivariant subcomponent. They obtained that using intrinsic equivariant neural networks, but you can try obtaining this using stochastic symmetrization instead. And an example I looked at in this paper was basically trying to learn the matrix inversion function. It's kind of a simple sort of toy example, but it's a non-trivial calculation to do. This function, it turns out, is equivariant with respect to the orthogonal group, really the full general linear group, but let's say for simplicity, the orthogonal group here. You can kind of check there's a suitable equivariance condition that is therefore kind of reasonable to impose on a model that is trying to learn this function. And you can kind of, you can run this and you get some results like this. So basically the green line, you should compare the green line with the green line here and the blue line with the blue line here. This blue line is using stochastic symmetrization along with kind of an unconstrained choice of this component that is required to be equivariant. So for this component that's equivariant in this method, we get that using like symmetrization, whereas for this dashed blue one, they use a particular intrinsically equivariant model, and essentially, as the size of the problem increases, stochastic symmetrization gets consistently lower loss. Similarly, this green one is sort of matched up with this other green one here. It actually wasn't possible on the hardware I had to run this at the full scale of, like, this is 64-dimensional matrix inversion, because this method is very memory hungry and sort of used all the VRAM that I had available. but it's sort of already starting to do worse than kind of stochastic symmetrization here at the sort of lower problem dimension. And these are sort of these baselines at the top here are kind of just this top one is a model that doesn't involve any equivariance constraints at all. So you would naturally expect that to do kind of worse. And indeed, that's the case. It's just sort of an unconstrained neural network. And this one here is using another another sort of symmetrization method as well. So stochastic symmetrization works. I'm going to mention briefly one other work that's kind of very recent as well, which basically applies this to diffusion modeling with these co-authors of mine as well, Leo, Kia, and EY from Oxford. Basically, I'll give a very high-level overview of this. This problem of diffusion modeling that you've potentially heard of is basically shown here. Essentially, you have two processes: a forward noising process and a backwards process that you try to essentially align through training. The idea is that the forward noising process starts with the distribution of the data and then kind of progressively adds noise to it, so that eventually at time t it is a Gaussian, and then the reverse process starts with a Gaussian distribution, and essentially the goal is to make it kind of iteratively recover the original image, or sort of the distribution of the data from that basically appears on this in this forward model. And in many of these applications, often it's of interest to have this reverse process be equivariant, particularly for diffusion modeling that's used for molecular data, such as, for example, AlphaFold 2 is the diffusion model that involved an equivariant reverse process. Previous work has enforced this by using intrinsic equivariant neural networks, intrinsically equivariant components. They've basically taken this backwards process to be Gaussian with mean function mu, which is given by an intrinsically equivariant neural network, like a graph neural network or some other architecture. Essentially, in this paper, we just basically obtain this reverse process by symmetrization. So we just use this out of the box like so. And it turns out that this leads to a sampling process, a training procedure that kind of looks like this. It's very similar to the original sort of diffusion training procedure, where you don't have these kinds of symmetrization, this kind of symmetrization procedure added on top. Basically adds this kind of these additional lines here. And otherwise looks essentially the same. Effectively, a standard diffusion would be basically this, where you don't have these R's appearing instead. And it kind of resembles, basically, you can sort of think of this as like a learned data augmentation that is also deployed at sampling time. So essentially, this R that you get is kind of a random rotation of your input at each layer that's applied to this epsilon component here, which is a neural network. This thing here basically corresponds to the gamma that I showed you from an earlier slide, but it's kind of the high level idea. You can think of more generally what these stochastic symmetrization methods are doing is kind of a generalization of data augmentation. Great, and so we get some results. I won't go through this in detail in the interest of time, but basically, effectively, we sort of applied our method. We sort of took a model that involved an intrinsically equivariant neural network as part of this reverse process, and we essentially just substituted in our reverse process instead, and kept everything else the same. And so the point of comparison there is basically these two lines here. The sort of baseline model had this score is kind of what people care about. This is molecular stability. This was sort of the baseline model before we did this substitution that, while it's still using this intrinsic component, and then we substituted in our thing and improved that score. Great. Okay, so then to conclude, I think overall, like what's the kind of takeaway from this? From my own perspective, like my view of this is that I think Markov categories provide very powerful and very elegant conceptual tools to let us reason at the level of abstraction that we actually care about. So we can kind of focus on doing the kind of reasoning that we're interested in rather than worrying about low-level kind of technical details that really don't say very much about, you know, the actual method that we're going to end up implementing. I would claim that the symbols we write down become more rigorous. They actually really like do match like this sort of, I guess, I don't know, there's probably no other way to say that it is sort of more rigorous using Markov categories. But at the same time, the concepts become more intuitive. So in a sense, at least in this context that I've looked at this, I think you do get a best of both worlds benefit once you do the sort of upfront costs of kind of learning the framework and kind of seeing how to use it. And yeah, I guess I would claim the three models become closer together as a result, which I think is quite cool and quite exciting. So yeah, thanks very much. That's everything for me.
Thank you so much, guys. Any questions for Rob or Paolo?
Yes, I got a question. So in one of the slides, you mentioned two questions. First is how can we obtain a process of symmetrization of any random map? Another question is whether it's enough, whether this symmetrization process can capture everything that we care about. And during your talk, it seems to me that you got both answers to both questions, right? Actually, you got the process of symmetrization, and then you can prove a theorem that says every map that's equivariant can be obtained by this process. If I understand that correctly.
So I tried to be a bit careful. I was a bit of a lawyer on that one. So it is true. So I would claim the answer is yes, that basically this does show that it's kind of everything. The precise statement is really this where was it? Sorry, it's this one here. So the precise statement is that every symmetrization procedure defined in this sense, you have to be willing to accept like the definition I've provided, but I think it's a reasonable one. Can be written like this, where you first of all apply this bijection and then you apply some function. Now, the symmetrization procedures that I guess people use involve a specific choice of this function, which is precomposition. And that's not every function. So in theory, there could be a function here that is not precomposition. Certainly, every symmetrization procedure will have this form, but then not every symmetrization procedure will have this form. I would say, though, it's every like obvious way of obtaining a symmetrization procedure has this form. And there's actually a precise statement you can give using the innate lemma, which is that every symmetrization procedure that is natural in Y has this form where you use precomposition. So I don't know if that makes sense, but yeah, there's a slight caveat in that in theory, there are more functions here, but without additional structure to kind of tell you how to kind of choose one, I think precomposition is sort of the only natural way. And I think as evidence for that, like all of these previous methods people have worked on can be expressed using this, I think inevitably so because they work at this high level of generality where they don't want to make these additional assumptions about the group and everything. I don't know if that answers your question, but yeah, it's in a chat.
Yes, I think that answers another question that I have in my head but didn't express. So actually the question I want to ask is whether it is true that every morphism in CG from X alpha X to Y alpha Y can be represented by a morphism in CXY. So by this process, we capture everything that can be equivalent by trying everything that we can write down randomly in category C from X to Y.
I think that if I'm understanding correctly, I think that this answers that question. So basically, so this set, if you just think of these as sets, the CGXY and CXY, they're just sets. So this is actually strictly it's a subset of this. It's always this thing is always a subset of
Okay.
this. So if this property holds, then sim is surjective, which I think is what you're saying. So this is kind of one reason that you might want this property to actually hold, because it ensures that the symmetrization procedure can express every morphism in its codomain. And then this is kind of how you enforce that, I guess.
Okay.
Is that yeah, cool.
Yes, thank you.
Paolo added a comment on the chat. Am I correct?
But I can't read that.
I just wanted to say, like, since by UNIDA we have that if we want this procedure to be natural in X and Y, then it's got to be some form of precomposition. We do want the kind of naturality. Usually, it's a little bit like equivariance, in the sense that it respects some kind of symmetry. In this case, it kind of says that it doesn't look into our data; it makes distinction based on the content, but it only depends on the actual structure of the product. So one could maybe construct a certain equivariant map that says something like, if you rotate by this angle, do this particular thing. But if you rotate this other thing by this angle, do this other particular thing. I imagine something like, I don't know, if it's a banana, rotate it accordingly. And if it's an orange, just send everything to a single point. That doesn't break its symmetry, but it kind of breaks the looking inside and see what fruit it is. So in order to avoid all these kind of, how do I say, hand-forced examples, then one usually wants to do naturality. And since usually one builds your electro exactly because one wants to not look at the data, be somewhat blind to the data. Just we don't know what the inner workings on the unit are going to be for each type of data. The naturality is a convenient constraint for one wants.
Okay, I see. Thank you. That clears my mind.
Any other question? All right. This is very, very exciting. I mean, you have already nice results, but I'm excited to see what are the next things, especially now with these connections with diffusion and generative AI. I think so many things to explore. Thank you so much, guys, for coming and giving the talk. I look forward to meeting you in 3D, actually. We should catch up.
Sure, yeah,
very much. Yeah. Thanks as well.